So today we're going to look at properties in graphing rational functions. We're going to find all of the pieces that would fall on the graph without actually looking at the graph. So we're going to do it all algebraically. Tomorrow you'll get to pair it with some graphs, but today we're just going to talk about the definitions and how to find these pieces. So some of the things you already know how to find. You already know how to find horizontal asymptote, vertical asymptote, and the removable discontinuity or holes. We haven't really talked about y-intercepts, x-intercepts, or domain and range. So let's start. So the y-intercept, no matter what kind of equation you have, the y-intercept happens in an ordered pair. It's a point on the graph where the x value is 0 because it happens somewhere on the y-axis. And everywhere on the y-axis, x is 0. So we want to know where would this equation have an x value of 0, and when it does, what is the y value tied to it? So all we have to do is we need to find the function when x is 0. So that means we're going to replace all of our x's with 0. Now, to simplify, so my function where x is 0 is equal to 3 times 0 squared is 0 plus 0 is 0. So I have minus 4 left on top. On the bottom, 2 times 0 squared is 0, minus 7 times 0 is 0, plus 5. So when x is 0, y is negative 4/5. So my y-intercept happens at 0, negative 4/5. So if I graphed this equation, it would cross the y-axis at negative 4/5. All right? The x-intercept. The x-intercept happens anytime your graph has 0 for y because it's on the x-axis. And if I'm on the x-axis, my y value is 0. So I need to figure out what x has a y value of 0. So what you're going to do is you're going to say f of x is the same as y equals, right? So we're going to say 0 equals 3x squared plus x minus 4 all over 2x squared minus 7x plus 5. Now, think about your rules of fractions. A fraction will only equal 0 if you get 0 in the numerator and some other number in the denominator, because 0 divided by a number is going to give you 0. So the only way I get 0 for y here is if the numerator becomes 0. So I really only have to solve the top of the fraction. So I'm going to take 3x squared plus x minus 4 and figure out what would make it equal 0. This is a quadratic, so I need to factor it. Remember, when factoring, when a is not 1, it's 3. So 3 times negative 4, I need two numbers that multiply to negative 12 and add to 1. b is 1. So that would be 4 and negative 3 would work. So I can say x plus 4, x minus 3. But don't forget the very last rule of factoring says divide by a. So divide by 3, divide by 3. 4/3 doesn't simplify, so the 3 gets back, so it's 3x plus 4. And x minus 3 divided by 3 is x minus 1. I need to figure out when those would be 0. So I'm going to solve 3x plus 4 equals 0. And x minus 1 equals 0. So minus 4, 3x equals negative 4 divided by 3. So x equals negative 4/3. Okay, or x equals 1. Now, here's a big deal. You cannot say that either of these are the x-intercept until you check. So you've got to check. Because if one of these numbers that made the numerator 0, if it also makes the denominator 0, then it is not good. Because remember, in a fraction, if you have something over 0, that's undefined. So I need to check and make sure that these x values don't make the denominator 0. So 2x squared minus 7x plus 5. Let's check 1. So 2 times 1 squared minus 7 times 1 plus 5. So 1 squared is 1. So 2 times 1 minus 7 plus 5. So 2 minus 7 plus 5. 2 minus 7 is negative 5 plus 5 is 0. And that is not okay. So even though that number made the numerator 0, which would lead us to believe it's an x-intercept, it's really not because it also made the denominator 0. And if your denominator is ever 0, then that's not a good answer. It's undefined, okay? So we would also check negative 4/3. So if I plug in negative 4/3, I don't know what number that gives you. I didn't do it, but it would not be 0. So 2 times negative 4/3 squared minus 7 times negative 4/3 plus 5 does not give you 0. So x equals negative 4/3 is a good x-intercept. So we would say that our x-intercept is, answer, x is negative 4/3, y is 0. That's your x-intercept. Okay, the removable discontinuity or the whole. Remember when you find wholes, you factor the numerator and the denominator, and then you figure out if they share any factors, right? So we already factored the numerator. We factored it to 3x plus 4, x minus 1. Now our denominator is 2x squared and minus 7x plus 5. So we need to factor the denominator. So 2 times 5 is 10. I need two numbers to multiply to 10 and add to negative 7. So negative 2 and negative 5. So x minus 2, x minus 5. So really, I have 3x plus 4. Oh, divide by a. Divide by a. Don't forget to divide by a. So that's x minus 1 times 2x minus 5. So my numerator is 3x plus 4 times x minus 1. My denominator, that's hard to read, is x minus 1 and 2x minus 5. Now, when we're trying to find the whole, you want to see if you have anything that's the same. The removable discontinuity is the same as a whole. So I have x minus 1 in the numerator and the denominator, which means I have a whole where x minus 1 equals 0. So x equals 1 is where my whole falls, okay? Now, at this point, that's all we've done with the whole. But a whole is really a point on the graph. So in order to name the whole, I need to know the x value and the y value. I know the x value is 1. I need to know what the y value is. Here's your steps for that. When you want to find the y value of your whole, you're going to pretend that the factors that gave you the whole don't exist. And then substitute the x value into the others. So when I pretend those don't exist, then I have 3x plus 4 over 2x minus 5 left. I'm going to replace my x's with 1. Because that's the number I found for x. So 3 times 1 is 3 plus 4. 2 times 1 is 2 minus 5. That's 7 over negative 3. So the y value, when my whole is at x is 1, the y value is negative 7/3. So far I know that I have a y-intercept at 0, negative 4/5, an x-intercept at negative 4, 0, and a whole, or removable discontinuity, where x is 1 and y is negative 7/3. All right, let's keep going. Horizontal asymptote. Horizontal asymptote, we know there's lots of rules for, right? So we know that there's bigger on bottom is 0, bigger on top is none, and so exponents are the same, divide coefficients, right? So if I look at my original thing, the exponents are both 2, so there's a degree 2 on top and bottom. So my my horizontal asymptote is y equals, divide the coefficients 3 over 2, and that is what you're left with. The vertical asymptote, remember we make the denominator 0. But when I look at, so I'm going to look down here where I already separated it. So I already found out that this is 3x plus 4, x minus 1 over x minus 1, 2x minus 5. I already figured out that x minus 1 is a whole. So the vertical asymptote is only 2x minus 5. So 2x minus 5 equals 0. Add 5. So 2x equals 5. Divide by 2. So x equals 5/2 is the vertical asymptote. Okay. Now, let's talk about domain and range. So domain is all of the x's that I would ever touch in a graph, right? Now, what's kind of weird about that is when I talk about the domains, I'm talking about all the x's. Well, I always assume that a graph will hit all x's, negative to positive infinity. But I know them I have where x equals 5/2, there's a vertical asymptote. And remember, an asymptote is something you approach but you never touch. So I'm not ever going to touch 5/2. The other x value I know that is not good is when I have a hole. When you have a hole, then that's a point that really isn't on your graph, right? You get close to that point, but then there's like this gap in the graph. So I have to assume that my graph, this equation, would touch any x possible except when x is 1 and when x is 5/2. So I'm going to say that my domain is from negative infinity, and it's going to go all the way until I get to positive 1. Union, so we're going to take a jump at 1. I can't include 1. But then we're going to pick it back up and say I can include anything from 1 to 5/2. Union, so also include. So at 5/2, that's where my asymptote is. So my graph is going to pick up and start back up somewhere else. And it's going to go 5/2 to infinity. So I am going from negative to positive infinity, but I don't actually touch where I have a hole, and I don't actually touch where I have an asymptote. So I have to include everything except for those values, okay? And that's why we use parentheses. Remember, if we were going to include this one, then we'd use a bracket. But because we're not including it, it's parentheses. All right, now let's talk about the range. So the range is all the y values, and I have to assume that my range goes from negative to positive infinity. But I need to look at what y values can't be included. So I know that there's a horizontal asymptote where y is 3/2. Horizontal asymptotes technically can be crossed, but that's something you would learn later. So we're still assuming that we're not actually going to touch this horizontal asymptote. We also can't touch the hole, so I need to include the y value of the hole, not in my range. So my range, we're going to go from negative infinity all the way until you get to negative 7/3. Then you're going to stop, pick your graph up, and you're going to continue from negative 7/3 all the way until you get to 3/2. Then your graph will stop, you will pick it back up, and you'll go from 3/2 to infinity. Okay? All right, so that's a lot of information. But like I said, some of it you're already familiar with. We just added a couple things to it. We're going to do one more example just because some of them can be kind of weird. All right, the y-intercept. Remember, the y-intercept happens when x is 0. You want to know the number for y. So if I take my function and replace x with 0, it's equal to 0 squared plus 3 times 0 over 0 squared minus 0. If I simplify that, I get 0 over 0, which is a little confusing, but remember, anytime you get 0 in the denominator, then this is an undefined situation, which means it doesn't happen. So if it doesn't happen, I do not have a y-intercept. So there is no y-intercept. So if you graphed this equation, you should never cross the y-axis. Or if it does look like it crosses the y-axis, then you know that the y-axis or the y-intercept is a hole because it's undefined and it doesn't really exist. The x-intercept happens, remembers, when you have some number for x and y is 0. So I have 0 equals x squared plus 3x over x squared minus x. And we talked about that you really only need to know where the numerator equals 0, because if the denominator equals 0, it would be undefined. So I'm going to take just the numerator, 0 equals x squared plus 3x. And in order to solve it, because it's x squared, I need to factor it, but I don't need to use my chart because there's only an a and a b term. So I can say 0 equals x times x plus 3. So we set them equal 0, x equals 0, and x plus, plus 3 equals 0, so x equals negative 3. Okay, now it looks like we have two x-intercepts, but I need to check. So if I take my denominator, I need it to not equal 0, because if it equals 0, then it's undefined and it's not really an x-intercept. So if I plug in 0, well, that does equal 0. So that is not a good answer because that makes my equation undefined. If I plug in -3, I need it to not equal 0. -3 squared is 9. Minus -3 is really plus 3. It's 12, which is not equal to 0, so we're good. So I do have an x-intercept at -3, 0. Okay, removable discontinuity. So we need to see if there's any holes. So I'm going to take my original equation, x squared plus 3x, over x squared minus x, right? Yeah. And I'm going to factor both the top and the bottom. So my numerator factors to x times x plus 3. My denominator factors to x times x minus 1. So it looks to me like I have a hole, this factor. So I have a hole where x equals 0. Now, which makes sense because we already found out that 0 makes it undefined. So somewhere we've got a hole where x is 0. So when x is 0, I need to find the y value of my hole. So remember to find the y value. Forget the matching factor exists. Take the rest of the fraction that you have and plug in 0 for x. So 0 plus 3 over 0 minus 1 is 3 over -1. It's -3. So I have a hole at 0, -3. Okay. Now, to talk about the horizontal asymptote, I look at the degrees. These are the same. So again, we're using the Eats DC. So if the exponents are the same, you divide the coefficients. So my coefficients are 1x squared over 1x squared, so I have an asymptote where y equals 1. The vertical asymptote, I need to know what makes the denominator 0. So if we look at how we already factored it, we had x plus 3 over x minus 1, and we found out that the x's are a removable discontinuity, so forget that. So that means that x minus 1 is my vertical asymptote. So I have a vertical asymptote where x equals 1. Okay, domain. Remember, the domain is all x's we ever could have, except the ones we just decided we were never going to touch. So I will never be at 0 because I have a hole there, and I'll never be where x is 1 because I have an asymptote, and you don't touch asymptotes. So my domain is going to go from -infinity to 0, and then pick up and move over and go from 0 to 1, and then pick up and go from 1 to infinity. Okay? And tomorrow you're going to see a visual of that. My range is all the y values, except for the ones that we just realized we can't touch. So I will never touch this horizontal asymptote, except every once in a while that does happen. So later on, don't be scared. And I will never touch this hole. So my range is going to go from -infinity to -3. It's going to pick back up and go from -3 to my asymptote at 1. And then it's going to pick back up and go from my asymptote to infinity.